Right, better strap yourselves in for this one. We've got a hemispherical bowl, and it tells us what the volume is in terms of H. It says T seconds, the height is H, and the volume is V. Water's leaking, so the volume's changing, and this gives us the rate of change of the volume in terms of the volume. And they want us to find out what the rate of change of the height is in terms of H. We're also going to have to do some partial fractions, and this is solving this differential equation because we want to get H in terms of T or T in terms of H. So here we go. It's June 2016, C34, question 13, last one on the paper. Right, so we'll start off. It tells us the rate change of the volume in terms of V. Well, we need to connect it to the dH over dt by writing the dV over t like this. You can imagine those dH kind of cancelling out. I've got dV over dt. So I want to know what dV over dH is. And I've got V in terms of H. So I'll just differentiate in terms of H. I'll multiply it out. I think it's the easiest way. You could use the product rule, but I'll just multiply it out and done it term by term. So dV over dH then that'll be 20 pi h, and then I'll just be pi h squared. And I'm gonna take an h out and a pi out as a factor, because then I'll give me 20 minus h there, and I'm kind of looking for that somewhere along the line. So the right hand side then, this is what the volume, a tenth of the volume is. Tenth of the volume. I've got minus 1 over 30 instead of a third, instead of that third. So I'm going to replace that dV over dH with what I found over here, and then multiply by dH over dt gives me minus a tenth of the volume, which is that. I'll do a bit of cancelling and get rid of a pi off both sides, and an h off here, one of those h's. So the dH over dt, well, I've got an h, 30 minus h over here, and I've got a 30, and I'm also going to have a 20 minus h on the bottom. So h, 30 minus h, which is good because that's what I want, and divided by that 20 minus h, and also got 30 on the bottom. So 30 times 20 minus h, which is also good because it's also what I want. Then we're going to write this in partial fractions. So we write it something over h plus something else over 30 minus h, multiplying through by that denominator. I can pick some values in. H is 0, so it's a good one, I think. Makes that term disappear. So I'll have 600 over here. 30 times 20 is 30a. Give me a is 20. And the putting h is 30 in, so I'll put anything in really. This has got to work for any value of h. I'll have 30 times minus 10. That term will disappear. 30b, and that gives me the b is equal to minus 10. So the partial fractions look like this. You might notice that that's the upside reciprocal of the fraction. With this. There's a very good reason for that, but we'll get to that in a moment. So given that h is 10 when t is 0, use your answers to A and B to find the time taken for the height of the water to fall to 5 centimetres. So I want to solve the differential equation. I've got some initial conditions. I'll be able to find out what the equation is connecting h and t, and find out when the height of the water is 5 centimetres. So we'll separate the variables out. The h is on the left hand side because that's on the top. I'll put the dt up here, so multiplying by the dt really. So h is on one side, t is on the other. There isn't any t's actually, but if there were, they'd be over this side. The left hand side, I'm going to multiply by the bottom of this fraction, so stick that up there and put this term down here. On the right hand side, I'll just have minus 1 because I've got rid of all that fraction. And then integrate both sides. I use the partial fractions that I found just before in part B, and they were those. And then I can do the integration then. This is 20 ln h. This one, it's going to be plus 10 ln 30 minus h. Because if I differentiate this, I will get that minus just there. And over here, I've just got minus t And don't forget plus c on one side when you're doing differential equations. Like I say, it tells me what h is when t is equal to 0. So subbing those in, 10 in for h and 0 in for t. I can change that 20 into 10 and put the 2 up there. So I've got ln 10 squared times by 10, and I've got 10 ln 20 here, which is the same as 10 times ln 100 times 20, so it's ln 2000. I've done it like an exact value rather than decimal for now. And then I want the time it takes for height of the waterfall to 5. So I put h is equal to 5 into here with the plus c. I get this, and you could stick it in the calculator then if you wanted to. I've simplified it a little bit. I took a 10 out as a factor. I've got ln 2000. I've got 2 ln 5, which I could write as ln 5 squared. So this bracket is ln 2000 divided by 25 divided by 25, which is actually 16 over 5. And when you stick that in the calculator, you get 11.6.